In this final lecture of Lesson 1, I would like to approach the construction of a measure on sequence spaces from a slightly different point of view, namely that of random variables and probabilistic processes. As we will see, we have actually done most of the work already, and it is now only more or less a matter of perspective, whether you want to approach everything from sequence spaces or through probabilistic processes on with discrete random variables to construct a measure on sequence spaces. In the former case, you use the Kara-Theodori extension theorem, and in the latter, that of probabilistic processes, that construction just becomes an instance of the Kolmogorov extension theorem. So we saw last time that the key to constructing a Borel measure on a sequence space a to the n is the following consistency requirement here for the binary alphabet, namely that the measure of a cylinder, sigma, is just the sum of the measures of its two extensions. And of course, if we have a more general alphabet, then this would be just the sum over all possible extensions according to the size of the alphabet here. So we can imagine a measure as some kind of a mass, and I'm going to draw a tree now upside down if you want, that starts with a certain mass at the empty sequence, and then let's say 1, just to be to keep it simple, a probability measure. And then this mass somehow distributes. So at the first splitting here, 0 and 1, could be now that the measure, let's say, splits into 1/4 to 0 and 3/4 to 1. So and then those two masses, 1/4 and 3/4, kind of split again individually. Now you can hear 0, 1, 0, 1, and now it could be that this here is a mass of maybe 1/12 here and 3/12 over here, and on the other hand here it's like 3/8 and 3/8. So here in the second step on this part it splits then evenly, and here it does not split evenly. But the important thing is that at each step the total mass is preserved. So if you can easily verify that the total sum of these fractions here is 1. So you can think of a probability distribution as somehow a mass trickling down along this tree here. That's why I drew it upside down, because you think of it, you put a mass here and then somehow, according to some probabilistic process, it kind of trickles along the branches of the tree. And at each point in time, the mass is that you started out with is preserved. So if we extend this tree now, whenever you cut through the tree like this and you collect the strings along the cut, then you always have this condition here satisfied, that the mass or measure of the strings in the cut equals 1. Arguably the easiest way to distribute a unit mass along the tree is to do it uniformly. So at each step you just split the mass uniformly between the two alternatives. So 1/2, 1/2, and then you would do this again. You would here have 1/4, 1/4, 1/4, and another quarter, and so on. So here you would have 1/8, and you do this successively. So then you would have the following measure. So the measure of a cylinder, sigma, would just be 2 to the minus the length of the cylinder. So this here is called the uniform distribution. And you can think of it as an analog of Lebesgue measure in Euclidean spaces, because every interval gets equal weight or measure. So the previous discussion where we saw that a probability distribution on the sequence space essentially amounts to letting a mass percolate or drip down a tree, suggests that we can look at the whole affair also from the point of view of random variables and discrete processes. So I want to do a brief review of this and show that it more or less leads to the same concepts. So let's start with a review of measurable functions. So we have a measure space. Now here, since classically random variables are denoted by capital X, I replace the symbol for a measure space by I replace X by omega, capital omega. And then we look at a function from this measure space into the real numbers, and that's called measurable if for all Borel sets in R, and we now mean the Borel sets with respect to the standard topology. So that just means that it's the topology generated by the open intervals. So if we have for every Borel set B in R, the pre-image of B under X, under our function, is an element of the sigma algebra of our measure space. And any measurable function or random variable X of that sort induces, in fact, a probability distribution on R, and just by pushing forward the probability distribution from our measure space to the real numbers, namely by defining P of B, where B now is a Borel set in R, is the same as mu, so the measure of the pre-image. So this pushes forward the probability or the measure from our space omega to R. And the usual notation for this is just to say Px is in B. So X now meaning here it's the random variable, so the random element. So a discrete random variable is one where our random variable takes values only in a discrete set. And from now on we mean discrete set, we just understand that it's either finite, it's the set of natural numbers, or the integers. In particular, a binary random variable is one where we only have two possible values, 0 or 1. And hence a binary random variable induces a probability distribution on the set 0, 1. A stochastic process now is a sequence of random variables, so x0, x1, x2, and all these random variables are defined over a common probability space, omega, a, and mu. And again, a discrete process just means now that all the xi take values in the same discrete set A. And again, for us, the most common situation will be where our set A is just the binary alphabet. So if we take values in our discrete set A, we also call such a process an A-valued process. So we assume that each xi takes values in our alphabet A, and we also say it's an A-valued process, or simply an A process. And now each of those random variables here induces a probability distribution on A. right? By just pushing forward the measure again from our underlying probability space. And from our sequence of random variables, we can now define their joint distribution as follows. So for a given natural number n, we define the probability p sub n that x0 takes value a0, x1 takes value a1, and up to xn minus 1 takes value a sub n minus 1, simply as the probability or the measure of the intersection of the pre-images of those AIs. And of course, each AI is assumed to be an element of our set A. And the sequence P sub n is called the distribution of the process. So it's a sequence of probability distributions. And we use the notation P sub n of a0 up to a sub n minus 1 for this term here, just the probability that x0 is equal to a0 up to x sub n minus 1 is equal to a sub n minus 1. And notice that this here is simply now a string over A. So what these P sub n are, there are probability distributions over the set A n, right? So to keep things simple, we assume again that A is the binary alphabet. And then we can do the following reasoning. Well, we know that for any string a0 up to an minus 1, this pre-image here, this intersection of pre-images, is disjoint from this intersection of pre-images. Notice here the difference is just that here we intersect with the pre-image of 0 with respect to xn, and here we intersect this set with the pre-image of 1 with respect to xn. So we continue the process. We look at one more random variable in the process. Well, these sets are disjoint, right? So that means since mu is a measure, it's an additive set function. That means here this probability, which is exactly the measure of this set here, the mu measure, right, is plus the probability here, which is the mu measure of this set. Together they add up to Pn sub a, Pn of a0 up to an minus 1, right? That just follows from the additivity of the measure function. So call this here double star, the property double star. But this property double star looks very familiar. It looks indeed very similar to this condition star we had in the previous lecture. So recall that condition was that for cylinder sets, mu of sigma is equal to mu of sigma extended by 0 plus mu of sigma extended by 1. And in fact, this similarity is not a coincidence, and that's due to the Kolmogorov extension theorem. So what does the Kolmogorov extension theorem say? Well, note that in the previous development, on the previous slides, it does not really matter what the underlying probability space, or that is our space omega a mu is, right? All that really matters is the distribution of the process. That is the measure that we obtain by pushing forward to our alphabet, and then the sequences of probability distributions Pn we get from that. Right? So that was the distribution of the process. So the original space is not really relevant to us. So the Kolmogorov extension theorem now constructs a space that is very convenient for us. So it constructs a space, an underlying space, from the distribution of a process, as long as this distribution, so that sequence of probability measures Pn, satisfies the consistency condition 2 star. And this underlying space is convenient for us in the sense that it is actually a measure on the full sequence space A to the n. So here's the statement of the Kolmogorov extension theorem. I'm not going to prove it. I'll refer you to any standard probability theory text. So suppose Pn is a sequence of probability measures, and each Pn is a measure on the set of strings of length n over A. It's a finite set if our set A is finite. We also assume that our Pn satisfy the consistency condition, double star, meaning that Pn of sigma, a string over A, is the sum of the Pn plus 1 of all the possible extensions of sigma in A. Then there exists a unique Borel probability measure, mu, on the sequence space A to the n, natural numbers here, so that mu of the cylinder sigma is just equal to the probability measure Pn of sigma. And that, of course, holds for all strings sigma over A. So as you can see from this theorem, the Kolmogorov extension theorem is just a different way of arriving at a measure on the sequence space, but the way is essentially the same, just now that we have this sequence of probability measures P sub n, and they have to satisfy this consistency condition double star. Before we had the consistency condition star. So in the last slide, I want to just compare the two approaches we had so far. So let's try to do a comparison between the sequence approach and the process approach. On the sequence side, we start with A-valued sequences. So x equals x0, x1, x2, and so on, where each xi is in A. And on the process side, we start with an A-valued random variable, a sequence of A-valued random variables. X0, x1, x2, capital X now. An A-valued sequence, or an A sequence, is often called a realization of a process. To obtain a measure on the sequence space A to the n, here on this side we started with a measure on the cylinders and added the consistency condition star, and then observe that we can extend this to the algebra via the consistency condition to the algebra of finite unions of cylinders. And then we use the Carathéodory extension theorem to obtain a measure mu on A to the n. So here, that was the Carathéodory. extension theorem. On the process side, we started with the joint distribution. The joint distributions, so those were probability measures Pn on a to the n, and then we had the consistency condition 2 star between those probability measures 2 star, and then you use the Kolmogorov extension theorem to arrive at the same measure. So if the PNs, the values of the PNs are the same as the values here of the measure on the cylinders, then here you arrive indeed at the same measure. So it's two different perspectives, but we arrive at the same concept in the end, a measure on the sequence space. And we will now frequently switch between the 2 points of view, between the process approach and just the sequence approach here.